Shall I get started? Shall I start?
Yes, sure. Yeah.
Oh, okay. Okay, so today I will go over some of the basics of critical phenomena which we will need to understand. Why is it interesting to perform a quantum quench across a critical point? So critical phenomena has got to do with phase transitions. You are familiar with phase transitions. For example, you have ice which melts, water which freezes, water which boils. And so this is a liquid gas system, which you are probably familiar with. Phase transitions are best described in terms of what is called a phase diagram. So here I have plotted the phase diagram of a solid liquid gas system with pressure on the y-axis and the temperature on the x-axis. And the phase diagram looks like this. This is the phase, which is a solid. This is a phase, which is a gas. And this is the phase, which is a liquid. What this phase diagram means is that at any given point on this diagram, with a given value of pressure and a given value of temperature, like this point which I've drawn right now, you are in the solid phase. For example, if it is water, the system in equilibrium will be ice. Similarly, if the point is over here, you will be in a liquid phase, which is water. These phases are separated from each other with lines. And in this case, these lines are called first order lines. What this really means is that as I go across any of these lines, there is a abrupt change in thermodynamic quantities. More specifically, the entropy per unit the volume. Now, you must have noticed I've drawn the diagram in a way that this particular line which separates the liquid and the gas actually ends at some point. Beyond that point, there is no distinction between liquid and a gas. On the other hand, the line which joins as a solid and a gas or a solid and a liquid, they don't end anywhere. They just keep going forever. This particular point is called a critical point. At the critical point, you cannot say whether the system is a liquid or a gas. And in fact, if you take a sample and heat it up to this critical temperature, this is the critical temperature Tc, and this is the critical pressure Pc, and apply a critical pressure, there is something which is called critical opulence. I mean, the whole thing looks like a very cloudy object. Light scatters very easily and very much at this particular point. So this is one example of a critical point, and we will try to understand some very universal behavior near this critical point. There is a second system which I will deal with, which is a system like a bar of iron, a magnetic system. For example, an iron bar. If you place such a system in the presence of a magnetic field, this bar will develop a magnetization at any temperature. But however, there is something very special about this system, that even if there is no magnetic field, for ferromagnetic systems, there is a magnetization even with H equal to 0. Now, in a magnet, what happens is that, of course, a magnet is composed of molecules, and the molecules have a dipole moment. So they are like little magnets themselves. A dipole, you can think of a tiny little compass. For a ferromagnetic system, what happens is that these little dipoles, which represent the little compasses which are associated with a molecule, they are all aligned exactly at 0 temperature. If you increase the temperature a little bit, some of them will be away from this common aligned direction. Some of them could also be a little bit different. But nevertheless, on the whole, there will be a net alignment. A net alignment means that a magnetization is non-vanishing. However, if I keep increasing the temperature, without any magnetic field, what happens is that for beyond a certain temperature, this is called the Curie point, this system looks like something like that. All the dipoles are randomly aligned. This means the magnetization, which is the average of the dipole moments over the entire sample, becomes 0. The point T equal to Tc at H equal to 0 is another example of a critical point. And one of our aims of this lecture would be to understand, for example, why these two very different systems, like the liquid gas system and the magnetic system, behave very similarly near the critical point. So this is what we would like to understand. Near critical point, both the systems we talked about behave very similarly. Now, I need to, in fact, make it a lot more concrete than what do I mean by behaving very similarly. Just as a prelude, let me draw a phase diagram of the magnetic system. The analog of the pressure of a magnet is now an external magnetic field H, and the temperature is the temperature. What happens is that all the way along the H equal to 0 to T equal to Tc, there is a first order line where things change discontinuously. It is easy to understand why this would be, things would change discontinuously. If I have a magnetic field, which is very small, but positive, so you're at a point somewhere here, because of the presence of an external magnetic field, all the dipoles would, for example, be aligned up. Whereas if the magnetic field was in the negative direction, all the dipoles would be aligned down. So if I imagine taking the sample and changing the magnetic field from positive in the z-axis to negative, something very suddenly happens as you cross H equal to 0. Namely, the net magnetization changes sign from positive to negative. So there is a discontinuity of this magnetization, and the discontinuity of the magnetization, in fact, goes to 0 as you approach the critical point. If I compute the 0 field and draw this as a function of the temperature, what you find is a line which looks like this. This again is the Curie point. When the temperature is higher than the Curie point, so for temperatures below the Curie point and the magnetic field which is 0, the system cannot really decide whether it's all the spins are going to be up, or all by spins I mean these dipoles, all the dipoles are going to be up, or all the dipoles are going to be down. Both have exactly the same energy and the same free energy. And the system, depending on tiny initial conditions, decides whether it's going to be up or down. This is an example of a very important phenomenon in physics, which is called spontaneous symmetry breaking. However, when the temperature is larger than the critical temperature, which is Tc, regardless of the magnetic fields, these dipoles are randomly allowed and the magnetization goes to 0. So how do we understand such a system? Of course, at the microscopic level, there are these molecules which have dipole moments, and you might wonder, well, I should write down what are the detailed theory of these dipoles, how do they interact with each other, what are the forces between them, and that's the way to describe the system. Now, this is technically correct, but this is not a good way to understand the physics which we are after. And this is a general lesson for any physical phenomenon. In fact, for example, consider just liquids, water flowing through a pipe that's made out of water molecules. If you want to understand, say, suppose you are, I don't know, an engineer, and you want to understand how liquid flows through, through that pipe, or you want to understand, you are aeronautical engineer, and you want to understand how the air flows as a plane is moving through the air. You don't go back to the microscopic description in terms of molecules and try to figure it out. You describe this in terms of an effective theory. An example of an effective theory in that case is hydrodynamics. The hydrodynamics is governed by its own laws. And these laws, of course, contain some parameters which are described by the microscopic physics, but the laws themselves are independent of the nature of the microscopic physics. In a similar fashion, for these magnetic systems, there is a way to describe the thermodynamic properties which was invented by Landau, who describe a notion of what is called an order parameter. And the basic idea is as follows. You take a large sample, for example, a lattice of points, as in a crystal. And imagine, for example, that each of these points corresponds to a spin which can be up or down. This is our simplest model of what I'll call a magnet. So now what you do, you take regions of this sample. In this case, I've drawn them by taking 4 of these sides and clumping them together, and take each of these regions and average over all the different spins. Now, I've drawn this with only 4 of these points in a given blob. But you can imagine, if the sample is very large, I mean, it contains 10 to the 23 points, you can take the number of points which are large enough, but small compared to the total number of points, in which case this average quantity can be described by a magnetization density which I'll call M of X. X is, for example, the location here. This is X. And this can be treated as the value of this can be treated as a real number. In other words, in this way of looking at it, this system can be described by a real scalar field, pretty much like a scalar potential describes an electromagnetic field. Where is such a description good? This description is good if you're making measurements not at the scale of the lattice spacing. You don't have a powerful enough microscope to see the individual points on the lattice, but you have a microscope which is good enough to see regions of space which say contain 10 to the 10 such points, which is much smaller than the total number of points, which is like 10 to the 23. For such measurements, I should be able to describe the physics in terms of this magnetization density. This is an example of an order, what is called an order parameter. Landau argued that I should be able to understand the thermodynamics by writing down the free energy of the system just to remind you, the free energy is the internal energy minus the temperature times the entropy of the system. In terms of this order parameter. So he said, what can the free energy be? The free energy will be an integral over all points, all these points which I have labeled by x. D is the number of space dimensions. It can have terms which do not depend on derivatives of m with respect to x, and it can have terms which contain gradients of this quantity m of x. Now, gradient of m of x is like in your course of electromagnetism, like the gradient of the potential is like the electric potential is like the electric field. And it can have, of course, other things. It can have del m to the power 4, all kinds of things you can imagine. So what Landau did was to say, to a lowest, to a very good approximation, I should be able to describe this by keeping the simplest terms, which you can imagine to write in the free energy. For the first pass, you consider gradients to be small. That means the magnetization, whatever it is, in the sample is roughly a constant over the sample. In that case, all we are concerned with, so then the free energy is nothing but the volume, let me call it U. This is like a potential times some function of m. And what would be the function of m be? I expand it for small m. I can expand it in terms of, let me write this thing down. And higher order terms. Now, notice one thing, that near the critical point here, the magnetization is small. So m, which is the magnetization density, is very small. So if the magnetization density is very small, m square will dominate over m4, m4 will dominate over m6. So this is a good kind of expansion. Now, this is something which has a symmetry under m going to minus m. And that symmetry can only be present. This symmetry can be present only if the external magnetic field is 0. When H is not equal to 0, you need to add terms which break the symmetry. And of course, the simplest term which will break the symmetry is a term which is like the magnetic field, which I'll call small h, because it's like a, or you can call it capital H, doesn't matter, times m. So let me add this to this, some h times m. So this is an ansatz. This is an assumption saying that, okay, I'll try to do this and I'll try to figure out whether I can describe the behavior near the critical point by a form of the free energy which looks like this. If I take a system at a finite temperature, thermodynamics tells you that I should minimize the free energy. So we need to find the minimum of U of M. Now these things are coefficients, and you must have noticed I have made these coefficients functions of temperature. So the idea is that the system is described by a potential like this. The potential is a power series expansion in the magnetization with coefficients which depend on temperature. So how do I find the minimum of this? So let's first take H equal to 0. So you need to find first the extrema at M0. And you would to require that the second derivative of the function at M equal to M0 is in fact positive. So that determines the minimum. Okay. When both A of t, now these coefficients, so I'll first start doing this by keeping the first few terms. When A and lambda are both positive, the potential U of M, of course, looks something like this. However, if the temperature is such that A of t is negative, then something interesting happens. Oops, sorry. Then the potential looks like that. The way to know that the potential looks like this is to consider the equation U prime of M equal to 0. So this means A of t M plus B plus lambda of t M cube equal to 0. This has three solutions, M equal to 0 and M equal to plus or minus A of t by lambda of t. And these non-trivial solutions are real only if A of t is negative. And this is precisely the situation here. If I look at the extrema, there is one atom equal to 0, and there are two others which appear when A of this must correspond to a situation where A of t is less than 0. And it is clear from the picture that the extrema, which has the minimum value of m, are in fact the ones which are given by these. So these have the minima of the potential. The other one is a maximum. So therefore, Landau argues that if the potential is like this, then there is a non-zero value of m, even in the absence of an external field, and therefore this must describe ferromagnetism. This simple but absolutely brilliant idea forms as a basis for a large amount of modern thinking in theoretical physics. I will not go into the ramifications of this beautiful thinking, but let me now focus what happens as we change the temperature so that A of t goes from negative values to positive values. So how can, so generically, by generically, I mean, I give you a function of t and I say at some value of t, a is negative, and some other values a of t is positive. And if this is a nice function, it better be smoothly goes from negative values to positive values. So generically, the form of the function must look something like this. So there is a value where a, t equal to tc, where a in fact vanishes. And as you can see from the nature of the curve, the generic situation has a of t goes as tc minus t near t equal to tc. The reason why I said that it should go, that generically it goes linearly in the difference between t and tc, is because if you choose from the space of all functions, if you choose randomly a function which vanishes at t equal to tc, what would you do? You would expand the function in a Taylor series in t minus tc. And there will be t minus tc whole square, or tc minus t in this case, tc minus t whole square, tc minus t whole cube with some coefficients. The function is characterized by the values of these coefficients. And generically, all the coefficients will be non-zero. It will take a bit of a work. It will take a bit of a fine-tuning to ensure that the coefficient, for example, of the linear term is 0. And those are special cases which I'll not deal with. If I just pick for random a function, it will near t equal to tc will be linear in t minus tc. So therefore, near t equal to cc, if I look at the formula for the magnetization, the solution of this equation u prime equal to 0, this solution there is a square root of this function of A of Tc. And assuming B of Tc is positive, you immediately realize that M0 goes as Tc minus T raised to the power half. Because A of T goes, and we call M0 goes a square root A of T by B of T.
This is lambda, right?
Yes, please. Say that again, please.
This is lambda, not B, right?
Oh, sorry.
Lambda of TC.
Lambda. You're right. Thank you. Okay. This number is an example of what is called an exponent, a critical exponent. And the transition which happens at T equal to Tc is called a critical transition or a continuous transition, because the magnetization goes to 0 continuously as T approaches Tc. So this is the magnetization as a function of temperature. And it is the behavior near here which is described by this equation. So we have obtained the behavior of the magnetization near the critical point, which is T equal to Tc, without too much work at all. And the lesson of this exercise is that this quantity behaves as some power of Tc minus T. And the significance of this calculation is that power is not an integer power, it's a fractional power. Why was it a fractional power? Because of this relationship, and because the parameters which describe the free energy are assumed to be analytic in T minus Tc. Okay? You can go ahead and calculate other thermodynamic quantities from this. For example, the specific heat, which is some derivative, some two derivatives of the free energy, and they will all be described as some powers of T minus Tc. So there are thermodynamic quantities behave as some powers of T minus Tc as T approaches Tc. So this is the first aspect, first important property of a critical point. Let me now come to the key property of a critical point. And this has got to do with correlations. I'll first describe what is the meaning of correlations in qualitative terms. You have a sample, and suppose you are in the magnetized phase. So there are these little dipoles here, which are by and large aligned like this. Some of them are like that. But overall, they all align in some direction. Now, why does a magnet behave like a magnet? It behaves like a magnet because these little dipoles have interactions between them, and the interactions are such that the energy is lower if the dipoles are parallel to each other. So this is called a ferromagnetic interaction. There are cases, in fact, very interesting cases, where the energy is lower if the dipoles are oppositely aligned. So these two dipoles, which are drawn by a circle next to each other, they are all aligned in the same direction. So they are in the lowest possible energy state. And so are these two. These two dipoles are not in the lowest energy state. They have a slightly lower energy because they are not aligned. Now, suppose I do the following. I take, say, one of these and change the direction by hand into something where it is naturally present. So now the point is that this creates a disturbance in the system, because you have by hand made a change which is called a fluctuation. What causes the fluctuation? Because the system is in contact with a thermal bath, and the whole purpose of a thermal bath is to make sure you have available energy which you can spend. And what does an energy do? It can excite the system. In this case, the excitations can appear as neighboring dipoles not being aligned. So you create a little excitation in this region. And of course, what will happen is that this excitation will have effect throughout the sample. Because you have done this, this one, the next two or these two also are in a higher energy state, and they'll also try to align themselves, because everything would like to go to the lowest energy state. So if this tries to align themselves like that, then the problem comes with these three. And yes, as you can see, this kind of disturbance propagates throughout the sample. Okay. You can now try to come up with a measure. So this is that means that a small change here causes changes throughout the sample, for example, here. And you would like to know how much of a change can be made in this particular fashion. This is measured by something called a correlation function. And I'll not describe what a correlation function is. The way you do this is you say that your magnetization, now I include dependence on X, is whatever value you have, and something which I called a fluctuation. And what you measure is the average, the thermal average X and eta of Y. If you're not familiar with this statistical mechanics terminology, don't bother. Just rest assured, there is a quantity which measures this kind of correlation between points which are far separated. And the result of this Landau theory is the following. When T is not equal to Tc, this correlation function, I'll call whatever it is, so I'll not even call this eta, has a property that it goes as e to the this times m x minus y for x minus y, which is the distance between the points large enough. And in this particular cases, this happens whether t is greater than tc or t is less than tc. Except this m is determined in terms of a, the functions a of t and lambda of t. I'll not even write down what that thing is. But something very drastic happens when t is exactly equal to tc. When t is exactly equal to tc, this function, instead of exponentially dying off at large distances, goes as a power law. And I'll call this power just by name 2 times delta. Delta is some number which is determined by the theory. Now it is clear that if I make a change here and measure the effect of this change at some other point, and if the other point is very, very far away, the effect will be very small. The question is, how does the effect decrease as you increase the distance between the points? And there is a huge difference between the way it does that away from the critical point and exactly at the critical point. If we draw these curves as a function of the distance between the points, this is an exponential. For large distances, it goes to 0 very fast. So this is at t not equal to tc. Whereas if the temperature is exactly at the critical temperature, this also goes to 0, but in a much slower fashion as a power law. Okay. The presence of power law correlations, there is a word for this, that power law correlations, power law fall off, is called long range correlations. An example of a long range correlation is what you see in electrostatics. In electrostatics, if you place a charge at some point and measure the effect of a charge at another point at a distance r, the effect goes as 1 upon r. This is Coulomb's law. On the other hand, there are other kinds of forces, in particular, for example, nuclear forces, where if you take 2 nucleons and ask what is the nature of the potential between 2 nucleus separated by some distance, that law is given by something like this. This is a Coulomb potential. This is called a Yukawa potential. This is the force between mesons, for example. Okay. It turns out that the key to understand the behavior, critical behavior near critical points, has got to do with these long-range correlations. The presence of long-range correlations is the key to understand critical phenomena. In this particular theory, in this Landau theory, it's called Landau-Ginzburg theory, it must be that this quantity M what is this quantity? This quantity M must go to 0 near the critical point. You define something called a correlation length called xi, which is basically 1 upon m, so that the behavior is really x minus y by xi. The meaning of this is that the distances are large compared to xi, the correlation is basically 0. But the distance is small compared to xi, the correlation is non-zero, as in fact given by a power law. You can calculate in this Landau theory, how does the correlation length behave as a function of the temperature? So near T equal to Tc, the correlation length goes as T minus Tc raised to the power minus half. This is another critical exponent. There are many other critical exponents which you can define in these systems. You can ask how, for example, the magnetic susceptibility depends as a function of temperature. You can ask how does the correlation length depend on an external magnetic field. All of these are powers of T minus Tc or the magnetic field, with some powers which are typically fractional, sometimes not even rational, which are called critical exponents. And the amazing thing about critical exponents is that many different systems have almost same critical exponent. And the task now is to understand, so a priori, a magnetic system has nothing to do with a liquid gas system. The analog, so the way you can, for example, in a magnetic system, you have an expression that the magnetization goes as Tc minus T raised to the some power. This power is usually called beta. So beta is equal to half in Landau theory. And in a liquid gas systems, beta is approximately half in experiments. And in liquid gas, the analog of M is the volume, the volume per particle minus the critical volume. The analog of temperature is temperature. You can ask, how does that go? Beta prime. And what one finds that beta prime is also very close to half. This is just as an example. And the point is to understand how come this happens. Why is it that so different systems behave similarly near the critical point? And I'll in the next, so how much more time do I have? 10 minutes?
Yeah, 10 minutes. I mean, we started a bit late.
Okay, yeah, she started late, right? And let me see how to do this. Okay. The key to understand thing is to understand the notion of what is called scaling. A correlation function which goes as some power, and let me call this power 2 times delta for reasons which I'll not go into. Has the property that if I rescale x to alpha x, y to alpha y, the lambda goes as 1 upon alpha to the power x. What does this mean? That if I measured the correlation function at some distance, like 1 centimeter, and I measure at a distance of 2 centimeters, then the two measurements are related by a simple power. So this is called scaling behavior. On the other hand, if this went an exponential of, say, x minus y by xi, as I have defined, and if I do this rescaling, I get that correlation function is not just some number multiplied by what you had, because it's a very non-trivial function. Rather, what is happening here, you need to rescale the correlation length itself. But the correlation length is just some function of temperature. There is no meaning of rescaling that. It's a property of power laws that if you scale the distances, the quantities also scale. So this is called scaling behavior. It turns out that the scaling behavior lies at the key of understanding universality. Now, I wrote down a theory which had, various potentials. It has some a times m square plus half lambda times m fourth. I don't know, mu times m6, do whatever you like. And all these quantities are some power. So these are all linear powers. This goes as some analytic powers of t minus tc. Near the critical point, what happens, and I surely don't have the time to explain why does it happen this way. The understanding of the reason behind what I'm going to say is in fact the theory of the renormalization group, is that if I rescale distances, I can get back the same physics if I also rescale the parameters. Let us denote these parameters collectively by gi. For example, in our example, g1 equal to a, g2 equal to lambda, g3 equal to mu, and so on. So what this statement means is that as I rescale distances by, say, x to x upon b, b is some number which is greater than 1. I've just chosen it to be greater than 1. Each of these, what happened? Sorry. Each of these gets rescaled by b to the some other power, which I call b minus delta I. D is the number of space dimension. The reason I wrote it like d minus delta I is just a convention. You could just call it some other number. These lambda I are called scaling dimensions. The important thing is that what turns out is that near the critical point, all these parameters, pretty much like the correlation function itself, get changed by this rescaling by just some powers of the scaling parameter. Okay. Now, what does rescaling mean? Rescaling means a change of the units by which you measure quantities. Rescaling, for example, distances, means that instead of using 1 centimeter as your unit, you can use 10 centimeters as your unit. It is entirely your choice of what you call a unit of measurement. Now, a correlation length is, of course, a length so a correlation length, remember, a correlation length is the distance beyond which there is no correlation between these elementary spins or dipoles, as I talked about. So clearly, see, it behaves like a length, and therefore the correlation length, which is a function of these parameters, must have the property that it just rescales. So under rescaling, x going to x upon b, I said that the result of this theory tells you that all these couplings go as d minus delta I, and the correlation length itself should go as b times I. Why? Because if I had a distance 5 centimeters, what that means, it is 5 times 1 centimeter. Right? Now, if I change my basic unit from 1 centimeter to, say, 2 centimeters, in terms of my new unit, the correlation length will be not 5, but 5 upon 2. So the scaling, it went as 1 upon b times x. That's why the correlation length goes as b times I. So combining this, you have an equation okay. What this equation tells you, that if I change my units, which I use to measure lengths, these parameters gi have to be changed accordingly with some powers. These lambda i's are some numbers. And if I just take in the Landau theory some function u of m, there are infinite number of gi's. Okay. Now, clearly, so let me rewrite this equation again. This is a mathematical equation which I haven't derived, but I sort of indicated why such an equation has to be true. And B is arbitrary. Then clearly something is different if lambda I is less than D. Then since B is greater than 1, is greater than GI. Whereas lambda I is less than D, this quantity is less than GI. And if lambda I is equal to D, then of course B to the D minus delta I is exactly equal to GI. What does this mean? This means that those parameters which characterize the theory, characterize the material which I'm dealing with, each of these parameters come with a number, which is lambda I. It's called a scaling dimension, but never mind, whatever it is called. And depending whether that number is smaller or larger than D, the behavior of this parameter under rescalings is very different. Such objects, such things are called relevant parameters. These are called irrelevant parameters. And we will now try to understand why they are called relevant and irrelevant. Suppose I have a material there is only one relevant parameter and many irrelevant parameters. I'll call this relevant parameter GR, and I'll call this GI equal to 1, 2, maybe infinite number of irrelevant parameters. I don't even care. Now what I do, I start with this equation. And this equation is true for any value of B. I'm free to choose whatever B I like. So let's choose B to be, this is a clever choice, GR raised to the power 1 minus D minus delta R. So let's write down this equation. So actually, let me write this equation in terms of this GR. Okay. And I just now make this choice. What does this choice do? It puts this first thing to be 1. So I get an equation which tells you and 1 okay. Now you see what happens. As GR goes to 0, goes to 0, and Xi goes as gr raised to the power 1 minus dr, and that goes to infinity. I said a critical point is characterized by an infinite correlation length because the correlation function becomes a power law. And in this discussion, it appears a critical point must be described by this quantity gr going to 0. But see something very interesting. So long as I take gr goes to 0, it doesn't matter what the values of gi are. The correlation length is entirely determined in terms of gr. Why it didn't matter? Why does the values of gi didn't matter? Because this quantity over here is positive. And as gr becomes smaller and smaller, this entire quantity becomes closer and closer to 0, so its value doesn't matter. This is why gr is called a relevant parameter. It is relevant for the critical limit gr equal to 0. So this tells you that the critical limit, the critical point is gr goes to 0, and the critical limit is gr going to 0, and gr is relevant to this critical limit. GIs, the values of GI can be whatever they are. As long as I go to the critical limit, my answer doesn't depend at all on the values of GI. This is the key reason why the critical behavior of the theory of this object, whether it be a magnet or whether it be a liquid gas, depends only on the values of the relevant parameters. They do not depend on the values of irrelevant parameters. So if I have two systems which differ from each other by values of irrelevant parameters, both the systems will have the same critical behavior. Now, this does not explain, for example, why a liquid gas is similar to magnet, but it does explain why a magnet made out of iron would be very similar to a magnet made out of nickel near the critical point. Iron differs from nickel in many ways, in terms of the detailed crystal structure, in terms of detailed properties of the microscopic. So it must be true that all those detailed properties can be summarized as irrelevant parameters near the critical point. This is one aspect of what is called universality. Because of universality, one of the effects of universality is that if there is one correlation, if there is one relevant parameter, everything depends on one scale. What does this mean? Depending on one scale means is that so far as the critical behavior is concerned, there is only one quantity which characterizes that material which carries some dimensions. So there is only one physical quantity of relevance which is dimensional. And as you must be familiar, in many examples in physics, if there is only one quantity which carries some dimensions, then any other quantity can be determined by dimensional analysis. So the other quantities, the behavior of other quantities, are determined by dimensional analysis. So for example, if I know, so for example, in this case, it is convenient to choose xi as the single dimension full parameter. And if I want to know, so xi, for example, in this case, like goes as Tc minus, say T minus the magnitude of T minus Tc raised to the some number. This is called a critical exponent. It's called the correlation exponent. It's a number which is positive, so that as T goes to 0, xi goes to infinity. And some other quantity, for example, the energy. The energy density is another physical quantity. You determine what are the units of energy density, what are the dimensions in the sense of dimensional analysis. Okay. So the energy density will scale as some power of xi. This is some number. Because near the critical point, this is the only quantity which carries any dimension. Energy carries some dimension. We'll do a little more of a detailed dimensional analysis in the next lecture. So it must be determined as some power of xi. Whatever power is xi is determined by whatever kind of theory you are talking about. So this is a key property near the critical point which we are going to use. The whole point of critical phenomena is that it becomes some glorified form of dimensional analysis to the lowest order. And this is, of course, a very powerful statement to make, a very powerful thing, which is why the theory of critical phenomena is so powerful. Now, I have dealt with examples of what are called thermal critical point, where you reach the critical point where we're tuning the value of a parameter, which is the temperature. Nowadays, there's a lot of interest in what are called quantum critical points. They are called quantum critical points because they appear at 0 temperature, but some other parameter needs to be tuned to critical values to achieve an infinite correlation length, which is a critical point. Now, even though the origin of criticality is different for thermal and quantum critical point, the physics is pretty similar. And the main element of the physics which we are going to use is the fact that the correlation length diverges, and if the critical point is something which is called an ordinary critical point, is basically there is only one length scale which determines the physics, and therefore things are determined by dimensional analysis. The fact that the correlation length diverges has a consequence for quantum critical point. And a simple example of a quantum critical point is a, oh, I'm taking too long. I think I'll just finish. Is a theory which is like a scalar field theory, which I understand, which you have studied. This is a scalar field theory. If you find in this theory, if you calculate correlators, they go as e to the mx minus y. So the correlation length is 1 upon m. And so xi equal to 0 means a massless theory. And since for such a theory, the energy dispersion relation goes as k square plus m square, this means a massless theory has no energy gap. This is the crucial point which we will use tomorrow to understand quantum quench, why there's something interesting and non-trivial about quantum quench across such a critical point. Okay, I think I'll end here. It has been a bit too long, but I hope I gave you.
Oh, thank you very much. It was very interesting.
Okay.
It's a lot, long, but sweet a lot. Very nice. Questions? Comments or any? Yeah, I mean, this is very interesting. By the way, an interesting thing about gravitational systems are always in a critical point. Some gravitational systems. That's why you can always rescale them in terms of a dynamic time that depends only on the.
That's right. That's correct. Right. Okay. Of course, in a little over an hour, I described something which is usually described in a 500-page book. So I couldn't do justice at all, but I wanted at least to mention the main physical points which characterize a critical point, which will be important for us.
Of course. No, I mean, the gravitational systems are fairly complicated. Yeah, I remember Isaac Schlossman, he used to invite Ginsburg a long time ago in the 1990s to discuss critical points of gravitational systems analogies and so on. You ever met him when he used to go to Lexington, Ginsburg?
I'm sorry. I mean, can you please come close to the computer?
Did you ever meet Isaac Schlossman used to invite Ginsburg to Lexington to discuss critical phenomena and possible applications? You ever met him? I never did because I was
met Ginsburg. No, I never met Ginsburg. But I know that it was a good friend of Isaac. That's correct, right?
Yeah.
Right.
So we were discussing this business of gravitational systems. We always.
I think he had a lecture about this in 1999.
Oh,
okay. He didn't go very far because gravitational systems are really complicated.
This was before I came to Kentucky, so I think I wouldn't.
Okay. Same with me, by the way. I just heard from Isaac. I never.
Oh.
I never met.
Right. Yeah.
Okay, I guess because you guys need to, there's also a problem. Transportation to central Cairo is like nice at this point, other than the expensive Ubers and taxis. So I guess the people.
Okay, thank you very much.
So tomorrow, maybe.
Okay.
See you tomorrow.